Hey buddies, MoNaCo here. Fourth video in our Kinetics and Equilibrium unit. We are finishing potential energy diagrams. The third video was a preview, and now we're going to finish potential energy diagrams, go into all the details about endo and exothermic diagrams. So let's take it. Let's hit the ground running here. So identify all the parts of potential energy diagrams. We did a little bit of that last video. We're going to do more of that now. We're going to find activation energies, changes in heat, and the effect of a catalyst. Alright, so let's check it out. We already talked about our key terms. It's the same introduction as last video. We're going to get in more depth about potential energy diagrams. Just didn't want last video to be too long, so we cut it into two. Here we go. Endothermic potential energy diagrams. Endothermic reactions have positive delta H because they they absorb their heat. Endo, the heat enters the reaction. Product side is on the right, is always higher than the reactant side, meaning that energy is absorbed. Energy gets soaked up in this process. Now, we need to label some parts of this reaction diagram. Potential energy of reactants, potential energy of the products are the first things that we need to label. Now, sometimes you'll see numbers here. I'm going to just write in a couple for ease sake. Okay, so potential energy of the products and the reactants. Well, that is the reactants are the A, right over here on that side, and the products are the B on the right-hand side. Okay. So if the reactants were asked to have, what's the number, you'd say 100 kilojoules. Product would be 200 kilojoules. Activated complex would be 300 kilojoules. You see how this diagram doesn't have many arrows drawn on it? Sometimes the arrows are drawn in, sometimes they're not. I'll be drawing the arrows in on this one, and you should too. So we covered A and B. C, potential energy of the activated complex. Well, there's the activated complex. Potential energy of it is right there at the very peak of it. It's how much energy you got to get up to over the top of the hill to come down the other side to make the products. Check. D, activation energy of the forward reaction. So how much energy does it take to go forward? And that value is how much it takes to get to the top of the activated complex. Okay? So in this case, it's the difference between 100 to 300. So that's 200 kilojoules it takes to get to the top of the activated complex with the numbers that I wrote in. The activation energy of the reverse reaction is the same idea, but we're coming from the other side. The amount of energy it takes to get to the top of the activated complex coming back in the other direction. E there. Now, heat of the reaction is kind of important to remember. You don't get this equation on table T. You got to take the heat of the products minus the heat of the reactants to figure it out. So we look here. The products had a heat we drew in was about 200 kilojoules there. And the heat of the reactants had a heat of about 100 kilojoules. So delta H equals the heat of the products minus the heat of the reactants. So delta H in this case equals 200 because we drew it in, minus 100 because we drew it in. And that value is 100 kilojoules. It's a positive number, and endothermic values should have a positive, endothermic reactions should have a positive delta H. I really just determined the distance between this value and that value. So that is, we've got to label that F. F, heat of the reaction. So the heat of the reaction is always the difference between the two flattest portions of the graph. And it is represented by this equation, easily calculatable. Let's look at the opposite of an endothermic diagram, an exothermic one, where the energy is released. Moving forward. Oh, got to stop at the activated complex first, because no reaction happens without activation complex. It's the highest energy point in the reaction. It's where the full rearrangement of all the atoms and molecules occurs. It's where all the bonds are broken and reformed before products slide down the other side of the reaction diagram hill there. Must happen for the reaction to be successful. If you don't get enough energy, you're never going to get your reactants up over the hump to make product. It's never going to happen. Exothermic potential energy diagrams. These are the situations where delta H is negative because the heat is being released to the environment. Product side, the right-hand side, is always going to be lower than the reactant side. This meaning that the energy is released. If the reactants had this much energy and the products had this much energy, which is lower, it must have lost some, and the negative sign for delta H says that in chemistry speak. So we're going to label the same parts of the diagram as we did in the endothermic, but on the exothermic diagram. So the first part, potential energy of the reactants, potential energy of the products. They didn't change. The height of these lines did, but the actual positions didn't. A is always there, B always there. Potential energies taken care of. Let's write in some numbers again just for fun. 100, 200, 300. Just so that when we calculate delta H, we actually can see that the value for it and the sign correlate to the shape of this particular graph. Potential energy of the activated complex. Well, the activated complex is always in the middle, always the big hump of the reaction over the hill. Activation energy of the forward reaction. In this case, we have the arrow drawn in for us already, and it's the height of the reactants to the top of the activated complex. So there's our D, that arrow right there. And the reverse reaction, same thing. Products to the top of the activated complex. Sometimes the arrows and dashed lines are drawn in for you. Other times you have to do it yourself. Be prepared to do both. And let's see, F, heat of the reaction. Delta H, still, you don't have this equation, you got to memorize it. Heat of the products minus the heat of the reactants. So the heat of the products, delta H, heat of the products minus the heat of the reactants. So the products were 100 kilojoules minus the reactants were 200. Well, that equals negative 100 kilojoules. That's our delta H value, and it's the distance between the reactants and the products flat portions of the graph. So our F value is that arrow right there, and the sign for it is negative. Exothermic reactions, as we mentioned, have a negative delta H, so all is good in life. That is great. Now I think on the next page we've got to do a couple things. We have to ask ourselves, what does a catalyst do to the reactions and activation energy? Which letter quantities would it change within the diagram? And I want you to draw this in your chart. A catalyst doesn't change the heat of the reactants or the products, it just changes how much activation energy is needed. It's a tool. It's like a tunnel through the mountain. If you think of this as a mountain from the products village to the reactants village, you could either go up over the top of the mountain, it takes a lot of energy to do that, or if you make a tunnel through, it takes a lot of energy to make a tunnel, but the path is much shorter, faster, easier to get to now. So if we tunneled through the mountain and added a catalyst, the quantities that are changed are not the heat of the reactants or the heat of the products, but the activated complex is different. The height from the reactants to the top of the activated complex is different now, and the height of the products in the reverse reaction to the top of the activated complex is different now. You can see these numbers, these arrows will be shortened. So D, C, and E are the lettered quantities that would change if we added a catalyst. D, C, and E. How does the addition of a catalyst change the heat of the reaction? The overall delta H, does it increase it, decrease it, or does it remain the same? Let's look back at our picture. Delta H is the difference between the reactants and the products. That didn't actually change. So delta H does not get affected by the presence of a catalyst. Your starting position and your ending position doesn't change. The route by which you get from there to there does. So a catalyst does not change delta H. It remains the same. What are the benefits of adding a catalyst? Well, by adding a catalyst, you can make your reaction go faster with less activation energy. So imagine you're doing a reaction that takes a lot of energy to get up over the hump. If you add a catalyst, you won't have to put as much energy in yourself. And if you're in one of these industrial complexes across the street here, working in a chem lab, oftentimes you want your reaction to go fast, efficient, with the least amount of energy put in. So you add a catalyst to make it go more efficiently and quicker. What are the benefits to adding a catalyst? You speed up the rate, you lower activation energy. Okay. So that's some more details about potential energy diagrams. At this point, you should have a little bit more information about how potential energy diagrams are labeled, the specific areas that are of importance, activation energy, forward reaction and the reverse reaction, potential energy of products and reactants, the overall delta H of the reaction, and the effect of adding a catalyst. Practice pack pages, 5, 6, 7, 8, 4 of them. Kinetics practice prep in castlelearning.com. Do the 15 questions prep, then do the 10 question quiz after you've done your practice and reviewed your notes, of course. So, thanks for your time. See you later.